For this third example, we're going to look at the series from n equals 1 to infinity, and we have -1 to the n times the square root of n plus 1 minus the square root of n. This one, I'll tell you up front, it's going to be conditionally but not absolutely convergent. And before I get into testing for convergence, I want to make one small note here. We can rewrite what's in the parentheses here, the square root of n plus 1 minus the square root of n. I'm going to rewrite this, and I'm going to turn it into a fraction. And let me turn my pen on. There we go. So what I'm going to do is I'm going to put this over 1, and then I'm going to multiply by the conjugate. So I'm going to multiply by n plus 1, or the square root of n plus 1, plus the square root of n, top and bottom here. In the numerator, when you FOIL that out, you're going to have the square root of n plus 1 times itself, which is just n plus 1. Then the outside terms, you're going to get a plus the square root of n squared plus n. Then you get a minus the square root of n squared plus n, so those cancel. Then your final term, you're going to get minus n. So when all is said and done, you just have a 1 in the numerator. So I have 1 over the square root of n plus 1 plus the square root of n. And that's going to help when I test for absolute convergence. So like I said, this is not absolutely convergent, but we're going to use the limit comparison test to show that. I'm going to use the limit comparison test with 1 over the square root of n. And this is a p. This is a p-series where p is equal to 1/2, so we know that this diverges. So let's look at this now. We have the limit as n approaches infinity of our series, which is 1 over the square root of n plus 1 plus the square root of n, and that's over 1 over the square root of n. So I can rewrite this. I'm going to take the denominator and multiply by the reciprocal. So we end up with the limit as n approaches infinity of the square root of n over the square root of n plus 1 plus the square root of n. Now, we're going to multiply everything, or numerator and denominator, by the square root of n. This one takes a little bit of algebra, which gives us the limit as n approaches infinity of n over the square root of n squared plus n plus n. Now what I'm going to do is I'm going to divide through by n. So n divided by n is 1. And we'll have the same thing here in the denominator. Over here, when I take this radical and divide it by n, that would be the same thing as dividing by the square root of n squared. So I'm going to have the square root of n squared plus n over n squared down here. This will be plus 1. Because again, dividing by n, same thing as dividing by the square root of n squared. What that's going to let happen, let me write over here. Inside that radical, I've got now the square root of 1 plus 1 over n. Now when I take the limit, 1 over n, as n goes to infinity, is going to go to 0. So I have 1 over the square root of 1, which is 1, plus 1. So that gives me just 1/2. So by the limit comparison test, because I know already that 1 over the square root of n diverges, this tells me that my series here would also diverge. So it is not absolutely convergent. Okay, so if we were to eliminate the negative terms, make all the terms positive, it is not going to be absolutely convergent. However, it could still be conditionally convergent by the alternating series test. So, what are those 3 criteria? Well, looking at our u sub n values, and I can go back and look at this here. That's our u sub n. Since n is always going to be positive, the square root of n plus 1 minus the square root of n, that will always be positive. So that takes care of criteria number 1. For the second criteria, that it is going to be non-increasing. For this one, I'm going to show it to you with the function and taking the derivative of the function. So I'm looking at the alternating series test. And if I look at number 2 on that alternating series test, I'm going to define f of x to be the square root of x plus 1 minus the square root of x. So this is the alternate way to show that it's non-increasing. I'm going to take the derivative of this. So if I take the derivative of this, I get f prime of x is equal to 1/2 times x plus 1 to the negative 1/2 minus 1/2 x to the negative 1/2. And I want to see where that is less than or equal to 0. So that would show where it is non-increasing for what x values. If I take the negative 1/2 x to negative 1/2 and move it to the right, and while I'm doing that, I'm going to rewrite this slightly. I'm going to write 1 over 2 times the square root of x plus 1 less than or equal to 1 over 2 times the square root of x. I can multiply both sides by 2 and get rid of those 2's. And then if I cross multiply, I'm going to have the square root of x is less than or equal to the square root of x plus 1. And that's going to hold. We can actually square both sides, and it would be x is less than or equal to x plus 1. So that's going to hold true for all of our values here. So that shows that it is non-increasing. Okay, so that's number 2 for the alternating series test. The third one says that the limit needs to go to 0. So for part 3 of the alternating series test, I'm not going to use this form of u sub n, but I'm going to use this one here that we created. And as n goes to infinity, you can see that the denominator would also go to infinity. We'd have 1 over infinity, so that limit would be 0. So it does pass criteria 3. So this is conditionally convergent by the alternating series test. You can see some of these just require a little bit more work because you need to check both conditional and absolute convergence.